Well, again, I want to thank everyone for joining me today on today's webinar on Wednesday. Again, methods of applying a thermal load to your structural analysis in SOLIDWORKS Simulation. My name is Silvio Perez. I'm the Simulation Product Manager here for Hawk Creek Systems. I focus everything related to our structural tools, all our simulation tools, and very heavily involved in our CFD flow analysis, our plastics injection mold. So essentially pretty knowledgeable of, or have a lot of experience, I should say, with all our simulation tools. And the topic that I want to talk about today is more so letting you guys see, or having you guys recognize, the different ways that we can run a thermal stress analysis by either inputting the temperatures directly or utilizing Simulation Professional or Premium to do a thermal analysis, or maybe you have flow simulation to run a thermal analysis. And what I'm going to do is just kind of do an overview of what that interface looks like, how we can incorporate that information at the end of the day to get a stress result or a displacement result based on your thermal loads and your thermal conditions. All right, so regardless of what level you have in your simulation suite, whether you just have your basic linear static or full-blown nonlinear and flow simulation, then there's a lot of options that you do have in incorporating this thermal load that we're going to discuss here today. Okay, so for today's agenda, kind of just mention that right now, is incorporating a thermal load in a linear static analysis. So being able to see how far we can get when we're just running a linear static analysis. We're going to do the exact same thing, but then focus on how far we can get with a nonlinear static analysis, because there are a few options there available, since we are somewhat of a time dependent or have options to change things as a function of a time step. And then we'll get into running a thermal analysis from SimPro and being able to transfer those results into a linear or nonlinear structural analysis, and then being able to see and do the same thing from flow simulation. And then throughout that, I'll discuss what the difference between is a thermal study from SimPro and flow simulation, what you get with one option versus the other. All right, so hopefully you'll find this helpful in terms of the different avenues, the different ways we can approach a problem, and the different product lines that we have that can offer these different thermal conditions. So, I like showing this slide here because what you're going to see in this webinar really ties in to these bullets that I have presented here. Is why specifically use SOLIDWORKS analysis tools? Well, because you're already using SOLIDWORKS, hopefully you're having, you have a relatively good experience using the CAD tool. The simulation tools are no different, right? They're integrated within the software. They're powerful tools that are able to give you accurate results, yet the learning curve is a lot shorter because it's in the familiar environment. So that being said, it being integrated within the actual CAD makes things a lot easier, allows you to do a lot of what-if conditions. What if, my material is this, or my material is something else, or my thermal loads change. But the other part of the integration is that if you have a structural tool and then you have, a thermal condition that you want to apply to it, we can run those things in separate studies and then kind of combine it together, which is what we're going to see here today, right? If we were dealing with other simulation tools, there's going to be a lot of export stuff that you have to do, maybe a lot of resetup that you may have to do back in simulation. When you're working in the SOLIDWORKS simulation environment, things are able to communicate with each other very well, which is what we're going to demonstrate here today. And then, of course, hopefully you're utilizing your tech support. We would be your single source solution for anything simulation related, just like how you get help from SOLIDWORKS CAD. You would be able to get, you would be able to get help from your simulation as well. Okay. Excuse me. And this is more just laying out, again, all the different simulation products that we have that are all tied into a single environment, things that, the products that we offer, but also recognizing and realizing that, what we can run a CFD analysis and transfer certain results to maybe an FEA result, or, possibly you want a motion analysis and do the same thing. Again, all these things are all integrated within each other, are within the same environment of each other, where they'll be able to communicate, export and import different aspects of a study type to get a specific answer. And that's what we're gonna focus on today is the simulation SEA and the SOLIDWORKS Flow simulation, where I'll be running ultimately a structural analysis in either a linear, static, or nonlinear, but being able to transfer the thermal results from a simulation study or from a computational fluid dynamics tool like flow simulation. Okay, so here is the product breakdown as far as what you get with just the simulation tools. So with Simulation Standard, you get your basic functionality of being able to run a linear static study on your parts and your assemblies. Within that functionality, you may be more familiar with applying just a normal force or a pressure, but what you can also do with the linear static is being able to define an actual temperature load. So being able to say that a certain component or a certain face of a component has a specific temperature, and you want to see what the stresses are or how much it's going to deform or displace based on the thermal expansion that will be defined from your thermal, your material properties. Right? So we can do that directly with just a linear static study, but that's assuming that you know what those final temperatures are. What we're going to see in the demonstration is you may run into a situation where you need to set up an actual thermal analysis to see what the final temperatures are going to be to incorporate conditions of your different modes of heat transfer, like radiation, conduction, convection. These are real conditions that are going to affect the overall temperatures that we can apply in a thermal analysis within SimPro, and then being able to transfer off those final results back into a linear static analysis to see what those stresses and different deformations are based off those thermal conditions. And moving forward, moving up the ladder, we can do the exact same thing within Simulation Premium with the nonlinear study. Right? I'll talk about here what the difference between linear static and nonlinear is, but with the nonlinear study, we still get results of stress and displacement, where we can also input directly a temperature load on a specific base or a component, within your assembly, or we can also transfer in those thermal results from SimPro or even flow simulation. But because we're dealing with now nonlinear, which is a function of being able to incrementally see how stresses are being developed through the different time steps, we can kind of link a transient analysis from a thermal to a nonlinear. So it will make a little bit more sense once we get to that point. But just letting you know, from our simulation packages here, there's a lot of different options that we can incorporate a thermal result into a structural analysis. And the first one that I'm going to start off here is talking about a linear static analysis. Before we do so, you have to recognize that even though we're incorporating a thermal input, a temperature as our thermal load, as our load condition to get results as stress and displacement, we still need to recognize what the assumptions are of just a linear static analysis. One of them is that the material is going to behave linear elastically. So any result that you would see going above yield, or the yield defined based on your material, those results are probably not going to be very accurate, where we would need to maybe go into a nonlinear study. But if you are expecting or assuming that you're going to see small displacements, essentially no permanent deformation, or you're expecting that your materials are not going to go beyond yield, then a linear static study would be a good fit, and then you can run your normal study. So just recognizing that what the assumptions are of a linear study. For nonlinear, right, we can then define a stress strain curve. We can define these more complex material types where the material is going to behave a little bit more realistic. Therefore, the results after yield or post yield are going to be that much more accurate, versus where in linear static we kind of have to say it pretty much yielded, but the stress results that we get are essentially not really correct. Right? And therefore, in a nonlinear, we can account for a large deformation and being able to see or control contacts changing as components are moving along with loads and fixtures. So you get a little bit more functionality to give you a more realistic case. But in the grand scheme of things, you really just have to wonder, is my thermal condition going to cause a large displacement or a large deformation. Maybe in most cases, you're not going to be within that realm where you would be living in the linear static condition. And that's, essentially what I have here for my model. I don't really expect to see, with this PCB with a whole bunch of electronic components attached to it. What I'm concerned about is, how hot these components are getting, the heat sink, the chip, the transformer, all those components. And I want to see how hot they're getting, or based on my thermal input, is it stressing enough to the point where I may be concerned where things are getting close to yield, or things may be getting too hot or stressing in areas that I don't really want to see stress, like in these connection points of the chip, things like that. So these are the questions that I may want to ask myself in running a thermal stress analysis. So looking at one example here, looking at the first one, I created a linear static analysis. So I essentially turned on my simulation add-in and I turned on a static analysis. Again, assuming those assumptions that we just discussed. So a few things that we can do when we run a thermal stress analysis. If you're familiar with running just a regular static analysis, the setup is exactly the same thing. You go down the list and you can specify your actual materials, that are dedicated to the actual components. But since we're dealing with a thermal load input, there are a few added functionalities that you may want to be aware of. So if I just open up this first material of this chip that I specified as gold and edit that, I created a custom material. I could have used the default material, that's fine, but keep in mind that if I use like a default material, just kind of randomly grabbing one here, if I grab it with default material, first of all, the material properties are constant values, and it's something that I won't be able to edit. So if I wanted to customize the materials a little bit, I can create my own custom material and throw it in the custom materials folder, like what I did here. And you may notice that the properties are color-coded, right? So just as a reminder, the values in red are properties that are definitely needed to run this linear static analysis. So it definitely needs the elastic modulus, the Poisson's ratio, the density, and the yield strength. And then the properties in blue are potentially properties that may be required based on your boundary condition input. In this case, it will need the thermal expansion coefficient within this material, since we will be inputting a thermal load. All right, so this is a key element here that is required when running this thermal stress analysis. But the other thing that I want to point out here is that notice that a couple of these properties are temperature dependent. So what I have an option to do is, if you click in the actual box here, you can input the constant value here, or you can select temperature dependent, and it snaps me to the tables and curves where I can actually specify that property changing as a function of temperature. So what you're seeing here is just, some random data that I found that I input within the actual material. So when I run the actual, or when I input my boundary conditions of temperature and it falls within the range of the curve that I've defined, it's going to recognize what this elastic modulus is at that specific temperature, right? So we can make these properties a little bit more intelligent and focus a little bit more towards this thermal analysis here. So that's one thing that we can do with this linear static analysis, is being able to define these materials but make them temperature dependent as well. So what I did here was essentially applied materials for all the components as you would need to do and what you may already be familiar with, and you would get that nice green check letting us know that materials have been defined. And then we can move forward, since we're dealing with an assembly. We can specify our contacts. These would just be like assuming that things are just bonded or glued together. So I think that's an appropriate assumption for this case for now. So I'm just going to leave. I set up a couple of contact sets here between components and the board. But moving forward, we still need to have some sort of restraint. Keep in mind that we're in a structural analysis, meaning that we can't just have parts or assemblies free floating. We need to have some sort of contacts or fixture to restrain the model. And I just put a simple restraint here. I could have been I was a little lazy here. I could have, drilled out some holes, or, made some split lines and fixed the board in specific areas. I just fixed the entire bottom face of that board, but just a simple fixture there just to kind of prove the point. But then moving forward, the main thing that I want you to focus on is that in this environment where we can input a load like a force or a torque or pressure, we have the option here to input a temperature, right? And in doing so, you see that I've defined a couple already, and you have a couple options. So here, when you hover over in the blue box, it's letting us know that we can apply a temperature on a face, an edge, a vertex, or the actual component. In this case, I'm going to assume that the entire component is going to have a temperature of whatever I defined here, which was 62 degrees Celsius. So what this is saying is that, or what this is assuming is that you know what the final temperature is going to be of this component, and then you just want to know what the stresses are around that area due to that temperature, right? So we're not seeing, we have no control of the temperature changing as a function of time in this menu here. We're just saying this is the final temperature of this component. And the way we select the actual component itself is, notice that we have this feature tree that we can expand. You just find the component that you want to apply the temperature of the entire volume. Typically, that's what you want to do, specifying the temperature of the entire component itself. If that is not what's happening in real life, where maybe just a face or several faces have a specific temperature, then you can define them more than, you can have different temperature loads to accommodate different temperatures on the different faces. If you select this all exposed spaces, what this is going to do is going to pre-select literally all the exposed spaces that you can see graphically and auto-select them. So you have a few options there, but typically you want to apply the temperature or the heat power for the entire volume, where you can expand that feature tree and select the actual component from there. Okay, so you see that I did the same thing here for the heat sink and the chip, selected the actual component itself, and that's the only boundary condition that I can apply. But of course, it may be more complicated than that. You're not limited to being able to add an additional force or a torque or anything like that. You can incorporate all those elements together to get this final result. It's just a function of what your real life scenario is. So once you actually mesh and run the analysis, you get your typical results like stress, displacement, strain, right? And you see that obviously all I input was temperature loads at those two components. So that's where I'm going to see the most activity, the most, colors, if you will. And if we're looking at the overall stress plot, it's looking at, a max stress of 103 MPa. What I can then do is compare that to the yield strength of my board, the yield strength of the overall materials that I use, and I can determine whether if it's below yield, and if it's below yield, then we're going in the right direction. Then I don't really have anything to worry about this design or about the temperatures that this is going to see, right? If it's going above yield, then we may have a concern there where things are yielding, then I may need to graduate to a nonlinear analysis. But what we can do here, of course, is we can take a look at, see that there's a lot of stress activity there in the boundary between the heat sink and the board. I can take a look at the displacement here. And you see, of course, it's not really displacing a lot. So I don't expect to see anything moving too much, due to the temperature that I've applied here. But essentially what we can do is make these determinations of, is it close to yield? Is it expanding or deforming in a critical way that, that may not be meeting my design criteria? But at the end of the day, we can do that with just inputting a simple temperature, assuming we know what that final temperature is. One thing that I didn't mention here that I kind of skipped over accidentally is within the actual study properties, you would also, in the flow thermal effects, you would need to define what the reference temperature at zero strain. And what that means is, if I were to change this to degree C, essentially this is my starting point. This is the temperature when there's zero deformation within my component. So I like to think of it like almost like the starting point of the model, where there's no stress, but more so no displacement or no deformation within the actual model. So it's something that you may want to define, something that you may want to change based on your scenario, where at zero strain, at zero deformation, things may be a little bit hotter or a little bit cooler, and this will have an effect in the overall results if you play around with that number. Okay, so that's kind of step one of what we can do with just a linear static analysis, being able to input that external load, that temperature load. Now, moving forward, if I did need to create a nonlinear study or run it as a nonlinear problem, we have this capability that was presented to us in 2017 where I can copy study, and I can transfer those results, or excuse me, transfer the setup to a nonlinear study where I don't necessarily have to recreate a brand new nonlinear study and then recreate or copy or drag and drop. I can just say, hey, I want to transfer this static analysis setup to a nonlinear, and I can do so very easily with that copy study functionality. And that's what I did here with this nonlinear, where I'm going to kind of show you now what the difference is between now a linear static and what we can do now with the nonlinear. So you see that the setup is essentially the same. I have the same materials. I define the same contacts, so everything that I did in the linear static copied over, and I still have that temperature defined at those two components. But keep in mind that in a nonlinear analysis, the results that we get are a function of a time step. So if I look at the actual nonlinear properties, you see that I can control what the incremental time increments are going to be. So depending on how I adjust this, I will be able to see, what the stresses are at these different time steps. So that being said, when I go into the external load of one of these temperatures, you see that I define 62 degrees for that entire heat sink, but now I have this option here to vary with time. So in a nonlinear capability, what I can do is I can control when that temperature is essentially turning on and off, or to what degree that temperature is going to be. Reason being is because on the left-hand column, you see that I can control the time up to 1 second, which is like a pseudo time, 1 second. And then on the right-hand column is my multiplier. So what I'm really saying here is that at 0 seconds, this is going to see a temperature of 0 times whatever value I have here. So essentially 0 degrees C. At 0.5 seconds, at 50%, let's say, it's going to see the full temperature at 1 times this value here. So you see that I can control to any degree when this temperature is going to adjust and to what degree it's going to adjust to. So in that added capability, we can then run the analysis, and if we take a look at, let's say, the stress, notice on my cloud message here that I have results, and it's showing results at time 0.69 seconds. So what I'm essentially doing is, if I edit the definition of that stress plot, I can view the results up to any point of my analysis based on how I define my time steps in my nonlinear analysis. If I do it at 0.93 seconds, you'll see that my results may slightly change there, right? If I do it at kind of the beginning, towards the beginning there, and hit OK, you see that my results definitely changed as well, right? So what we're able to, the benefit of adding this time increment thermal input is being able to see how those stresses develop based on how I control that thermal load essentially being on at 50% in the middle of the runtime. I can do the same thing with the displacement plot here, and I can animate this, and you'll see what's happening is that the value is changing, so my color plot is changing as a function of time. And you see that it's essentially loading that in as a visual representation, right? We can do that the same thing in a stress analysis, and I see how the stresses are changing visually, or at least through the color plot, as that time is changing. So if you want to see how the stresses are being developed as it's changing within time, very easy to go within the definition of that plot and just selecting what time step you want to load in that result. Okay, so to recap so far, we've done a linear static, we've done a nonlinear, and all we've really been seeing is being able to directly include a thermal load, a final temperature, and apply it to specific components. In a nonlinear, we can do the exact same thing, but then have the control to being able to vary it with time. Okay, And again, that's assuming that you know what the final temperature is of your components. But what if you didn't know what that final temperature was? What if you needed to run an actual thermal analysis to account for conduction, the convection, or potentially radiation to get that final analysis? Or that final result. And that's where we may want to incorporate, a thermal analysis from SimPro or even flow simulation. If we focus on the thermal analysis within SimPro, you see that I can, depending on the license type I can then enable thermal analysis, and that's what I have here. And you'll notice based on my naming scheme here, we can run a steady state and we can run a transient analysis. So in the thermal analysis, you see that the setup tree is very similar, but now the functionalities or the inputs are slightly different. So starting from the top again, going into the study properties, you see by default it's going to be set as a steady state. So what that means is no matter how I define my thermal loads, my temperatures, my conduction, or excuse me, my convection, we're not going to see how the temperature is being developed. Essentially, what we're going to see is what the final temperature is internally. It's going to keep iterating until it converges to a result. So with the steady state analysis, we're just going to see what that final temperature is. So we can define the material definition there. You see that if I go into the actual, let me just pull this up here. If I go into the actual material definition, my material scheme, color scheme here changes, where now the properties that are definitely needed in a thermal analysis is the mass density and the thermal conductivity. And the nice thing about that is very similar to what we saw in the linear static, is that I can control the thermal conductivity as a function of temperature as well. So as the temperature is changing, the conductivity may change as well, so we can make that property a little bit more intelligent. So just keep in mind that we have that functionality that we can change within a thermal analysis as well. Okay, so I pretty much set up the same material definitions there for my linear static. And then we have our contacts, where in a linear static, we just assume everything was bonded. In a thermal atmosphere here, or thermal environment, we don't necessarily say, or we could say that things are bonded together, but what that means is that there's going to be perfect conduction between the bonded components. In real life, there may be some adhesive, some sort of thermal grease. Those are elements that you wouldn't necessarily physically model in CAD, but that will play a role in what the temperature distribution is between one component to the other. So what we can define here is our contact set, specifically a thermal resistant contact set. And just for the example here, what I defined was a contact between this transformer to the actual board, and then you input some sort of thermal resistance value. So if you have like thermal grease or an adhesive, this is something that you could potentially find as a spec within the material that you're using. And the difference between total and distribution is the units really. So the total of Kelvin per power, if you will. Distributed just means per unit area. So I associate that to like knowing either the force or the pressure, right? So, but at the end of the day, what we can define is numerically input some sort of resistance between those components to accurately account for the temperature distribution from that component to the board. All right. And then moving forward to the actual loads, you see that since we're in a thermal environment, we don't need to specifically input like forces or anything like that. We're inputting elements of a thermal analysis, which would be either temperature or convection, radiation, or some sort of heat power. So what I ended up defining here was I input for these components that are highlighting an actual physical temperature. So what that means is that those components are going to see a constant temperature of whatever value that I input, very similar to what we did in a linear static analysis. But the added benefit of running this thermal analysis is being able to do an actual heat power, where I can input a value in terms of watts, the actual heat power of these individual components. And that's essentially what I did for the rest of these components here. And then I want to add the element of actual convection. Maybe, this is going to, obviously this is going to release heat into the environment. What's going to be the convection? So one thing to note about convection and thermal analysis is when you edit the definition of that, you'll see that I have to input the actual convection coefficient value. So what that means is what we're assuming in a thermal analysis within SimPro is that the temperatures of the air, or the temperatures, are essentially not changing in this theoretical, if there was air actually involved in this environment. So essentially what this is saying is I'm defining what the actual convection rate is of these faces of these components. And if you're familiar with the thermal analysis, you may know that the convection values of one face versus another face of another component may be different. So we're making a pretty drastic guess here in terms of what this convection rate is for all the faces. I can add multiple convection components for each individual face, but that requires you to actually know what that convection value is. Because again, the major assumption that we're having in this FEA approach of a thermal analysis is that there is no air, there is no changing temperature of air, where we need to physically change or define what that convection value is. So it may be an iterative process that you do, somewhat of a educated guess, or you actually know what that value is based on lab testing that you've done, but just be aware that you're inputting what that value is. So I can apply those conditions, and then I can run my analysis and get my overall temperature results. And again, we're running a steady state problem here. So what that means is that I'm getting what the final temperature is based on these conditions that I've defined within these thermal loads here. Okay. So what I can then do within that is I can also run a transient analysis where I can easily duplicate this, go into my study properties, switch this to a transient analysis and say, well, I want to run this for, let's say, 300 seconds, and then I can input what my time increment is. And what that means is I'll be able to see results at the 10, 20, 30, 40 until we get 300 seconds. So what I'm asking for here really is I'm going to get 30 time steps that I'll be able to see the results for, and then essentially see how the temperature is changing as that time is increasing to 300 seconds. So nothing really different that we need to run or do, or setup-wise that we have to do different. The only thing that we need to define is an initial temperature, where I just define a normal temperature load, and you see that I pre-selected all the components that are active within this assembly, and saying that the initial temperature is 25 degrees C, and then that will be essentially our starting point, and then the results will be calculated for all the rest of the conditions here. So when I run the analysis, right, you see in this message that we're loading in the result at time equals 10 seconds. So at that very first time step, you see already that the max temperature is at 45 degrees C. Keep in mind that, again, when you input a thermal load, like an actual temperature load, it's a constant value from the beginning. So it's always going to be 35 or 45 degrees C based on what I defined here. So, but moving forward, if I go into the plot definition and see what's happening now, let's say at 70 seconds, and hit OK, you see that my temperature changes. My temperature changes for the heatsink and the overall board and the attachment there. And if I animate this, very similar to what we saw in the nonlinear study, you see that my temperature is changing as a function of time. So you can load in at 300 seconds and see what the final temperature is, and make your best judgment as far as whether that's meeting your design criteria as well. The other added benefit within the thermal analysis is that when you go into, let's say, heat power, you also have the option to vary that component as a function of time, like what we did in a linear static. In this case, I did not, though, right? But you do have the option of controlling what that temperature or what that heat power is doing as a function of time. But that's kind of step one of what we would do. Again, keep in mind that our overall goal is to run a structural analysis to get stress and displacement due to this now thermal result. So if I go into a nonlinear study here, and it doesn't necessarily have to be nonlinear, but if I go into my external load where I would set up my materials, my contacts, just like normal what we've been seeing before, when I right-click on external load, you see that I have the option here to select thermal effects. And all that's really going to do is snap me to my study properties, where I can then reference what temperature or what thermal study to incorporate within the analysis. So you will see this option in the linear static analysis as well, where you see if I select temperatures from thermal study, I can say, get my max temperature for my steady state. So if I reference the steady state analysis, it's just going to show me, or it's just going to reference what the max temperature is, what the final result was of that steady state. But if I ran a transient analysis and select that, it wakes up the time step option, where I can say, pull the temperature from time step number 50 or whatever it may be, and it will pull that temperature into that analysis. Or in this case, since we're referencing a nonlinear analysis where things are a function of a specific time step, where in a transient analysis, it's a function of a time step as well, I can select this option for each nonlinear time step, use temperature from corresponding time of transient thermal analysis. So essentially what that's saying is that it's going to try to do its best to try to match or interpolate the time step of the nonlinear and the time step of the thermal analysis, so that essentially those temperatures are being loaded in at the appropriate time. All right, so again, you're seeing how we can combine these different elements, these different study types, to narrow it down to this static analysis. And then again, we can input our zero strain temperature at 25. And then what we get here is our typical stress and displacement. But now, again, the main takeaway here is seeing how we can incorporate that thermal analysis where we may have not known what the final temperatures are into the overall, into the overall static analysis or nonlinear static analysis here. Okay, so those are the major elements that we can do, again, with this suite of simulation products here. Really what we did is we incorporated elements of either we're running a linear static or a nonlinear analysis, but we incorporated what we can do from a thermal analysis from SimPro into a static or a nonlinear problem. Okay. But there is another technique that we can do to run a thermal analysis. And it's by utilizing our flow simulation tool, our computational fluid dynamics tool, flow simulation. But you may want to ask, or you may be asking, well, why would I want to use flow simulation versus SimPro? What's the major difference? Well, the difference here is that the thermal analysis in SimPro is a FEA approach in terms of breaking up the model into these small elements, but it's not incorporating anything about air. Like there's no way for us to define like fans or saying that the temperature of air is changing or the direction or that thing. Essentially, there's no air component to this FEA approach. We're essentially assuming that those temperatures are not really going to have an effect due to that theoretical air. In a situation where air is a major component, where maybe defining an actual numeric value for convection could potentially be a problem, or you may not know what those values are, flow simulation essentially calculates that for you because it is accounting for air. All we need to define in flow simulation is what the direction, or what the orientation of the model is, and then it defines what direction gravity is, so heat is going to rise opposite of that. So you don't need to guess at what the convection value is. We're getting a more realistic thermal result due to these more realistic thermal conditions, specifically when we're dealing with natural convection. And then as far as, again, just what it is, it's a fluid flow heat transfer simulation tool that's also integrated within SOLIDWORKS. It's very powerful yet easy to use. There's a misconception that a computational fluid dynamics tool is more for like an analyst, where maybe you have your CAD designer that throws it over the fence to the actual analyst, but flow simulation utilizes the same concept of the normal simulation tools, where we're really bridging the gap between designer and getting these results. Right. So as far as what we get with flow simulation, again, it's a computational fluid dynamics tool where it allows us to do internal, external studies, see essentially fluid behavior, and it's a great tool for heat transfer problems as well. All right, so moving forward into the actual interface, that is something that I can turn on through my add-ins if you have the license type here. And I just want to briefly go over the general setup of this flow simulation study, specifically to run a thermal analysis. And you see that I've already set something up here, and I just kind of want to go down the list here. The interface is slightly different from SOLIDWORKS Simulation, but the overall workflow and the overall inputs are the same. So the first thing that we do here within flow simulation is that you can go through your wizard where it takes you into defining what physics are being involved, whether you want to do an internal or an external study, right, and what conditions do you want to apply based on your thermal analysis. So in this case, I want to account for heat conduction, and I want to account for natural convection. So natural convection is simple as defining the orientation of the model, and you see that gravity is pointing in the opposite positive y direction. So heat's going to rise opposite of that direction, and that's all we need to do. We don't need to define specifically what the convection rates are. We're just saying heat's going to rise opposite of that, and then account for all the other boundary conditions. So we go through the list. We can define what fluid is going to be incorporated here. Of course, it's going to be air. And then we can define initial conditions here as far as what our starting point is. In this case, I ran it as a steady state, but you do have the option to do a time-dependent or a transient analysis, very similar to what we saw in the SimPro. But if we run to the steady state, you see that we get this box, which is our computational domain, which is we can resize that. And what we're controlling there is when we actually mesh the model, it's breaking up not only the model, the geometry, but it's breaking up the actual fluid elements within this box here. So this is submerged in air, essentially. So that's what we're accounting for in the CFD tool. But you see that we can incorporate, material definitions very similar. We select the components graphically. We can define what those materials are. Flow simulation utilizes its own material database where I can go and utilize the predefined or create my own user-defined. What's nice about these the predefined materials is that a lot of these properties are driven by tables already, so they're not specifically constant values like in SOLIDWORKS Simulation. So if I go into the tables and curves, you see that specific heat, the thermal conductivity, as the temperature changes, the thermal conductivity changes as well. So these materials are a lot more intelligent in terms of adjusting its value from wherever it stands within this temperature value here. Right? So we can control that within flow, and then we can specify, what the heat sources are, whether we're applying a heat source on a face or a volume. And that's essentially what I did here, where I recreated what these conditions are for all those components, like what I did in simulation. But the added benefit within using flow simulation is defining these goals, so you can control what you're interested in seeing, what you're interested in learning from the analysis, and using that as a convergence, as a convergence criteria for your results. So you see that I may be interested in the temperature of the fluid or the overall temperature of certain components. So you have full control of what information you extract from the analysis. And once you run it, you can load in your results and see what your plots are doing or what your temperature is doing. And we can generate what's called a cut plot, which is taking a slice of the model, seeing what the temperature distribution is of not only the components, but of the fluid itself. And I can turn off the geometry very easily here to see what's going on. I can create multiple cut plots to take slices at different areas of the model, like what I did here. Now I'm cutting it in this direction, where I overlaid what direction heat is rising. So you see, this is what natural convection is giving us, is seeing the temperature coming off the geometry itself. And you see that it's going in the right direction there. All right, but these are elements that we can get in terms of seeing how hot these components are getting. But as far as taking it back to the actual structural analysis, I can then go into my flow simulation study tools, and I can say export results to simulation. So when I create a new study, I can reference that, where I can set up the exact same problem that I did before in the structural analysis, but now when I right-click on external load, I can then have the option to select flow effects, which again takes me into the properties, but now what I'm going to do is I'm going to import the temperature from my flow result where I just browse to the flow flow result file. And you see that we can do it at a steady state. If I ran a transient analysis within flow, I can do the same thing where if I go into the study properties and reference a temperature from a result file, you see that I can pick and choose what result file or what time step I'm going to reference a specific temperature, right? And you see that at this point, it's referencing the 0.6 time step, which is going to load in that result, and then I can run my traditional static analysis within and view my stress and displacement plots, now referencing the flow simulation results. Okay, so hopefully what you're getting out of this is seeing the different capabilities that we have available for us to be able to essentially either input these thermal conditions directly or being able to utilize our thermal analysis from SimPro, or if you have flow simulation, running that thermal analysis, but at the same time recognizing that it's all integrated within SOLIDWORKS and being able to get these final results, these thermal stress results based on those conditions. Okay, so that's all I really had for you today. Hopefully you found that okay. Definitely let me know if you have any questions with that, but that's essentially all I had for you. If you have any questions, feel free to send them over through the chat. If you have any other inquiries or anything like that where you need to contact technical support, or maybe you want to ask some questions to your local account manager, feel free to contact us here. If not, thanks for joining me today. Hopefully again you enjoyed it. I'll be sticking around here for any questions that you guys may have. If I don't hear from you, have a good day. Thanks a lot.